Hello class, these are our Algebra 2 notes for section 217, Graphs of Rational Functions. This is part 1. So graphs of rational equations are in the form p of x equals f of x over g of x, where f of x and g of x are both polynomials. So we talked a little bit about this the other day. These are polynomials in the numerator and denominator. So remember, a polynomial could be a quadratic. It could just be a constant. We could have 5 over a quadratic. And remember, the domain is where our denominator is not equal to 0. So our denominator cannot be equal to 0. Everywhere else you would have the domain. So for example, if I had a denominator that was x minus 4, x could be everything except 4. 4 minus 4 would make a 0. We'll talk a lot about that. So an equation that relates distance, rate, and time is d equals rt. I know you've used this a lot in a science class. And then going back to this idea of literal equations that we played around with the other day, I know if I'm solving for r, I am dividing both sides by t. And so that gives us the equation r equals d over t. So we're kind of using this equation, we're solving for different variables. And then if I wanted to solve that equation for t instead, then what I would do is divide both sides by r, and t would equal d over r. So I don't think we need to memorize them all. I think we just need to think about how literal equations work and how I could solve that if I wanted to. So I always just remember the distance equals rate times time, and then depending on what I'm doing, then I would go ahead and solve it. So example 1, the distance across the English Channel from Dover in England to Calais in France is 33.3 kilometers. Write an equation for C representing the time it takes to cross the English Channel as a function of the rate of travel in kilometers per hour. So we've got a distance. We know the distance is fixed, right? It's if we're going to swim across this channel, it's 33.3 kilometers. But if we swim really, really fast, that means we would have like a really high rate of speed, right? As we're swimming, we know it's not going to take very much time. But if we swim really, really slowly, it could take us a lot of time. And we're looking to write an equation representing time. So this is going to be time question mark. That's what we're finding as a function of the rate of travel. So we want to have t equals is what we want. So that means we're going to use our t equals d over r equation. So t equals d over r. And they're even writing it as t of r because t is a function of r. We have a number for distance. Our distance is 33.3. And then the rate is what we're trying to figure out. Like I said, if we swim really fast, then the time won't take very long. If we swim really, really slowly, it'll take us a lot of time. And we want to fill out this table. So first of all, what happens when we put 0 in for rate? Well, if we put in 0 for our rate, it doesn't really make sense because we still have to travel the 33.3 miles per hour, but we'll also never get there. Or sorry, 33 kilometers, not per hour, but just kilometers that we have to travel, but we won't get there. It doesn't really make sense. So if we plug in 0, we don't get an answer. It's undefined. So let's go ahead and write undefined. But if I plug in 2, well, that's going to be 33.3 over 2. So maybe we should write above here what we're doing. And then if we do 33.3 divided by 36. So let's see. If we divide by 2, we get 16.65. So that means if we travel at a rate of 2 kilometers per hour, it would take us 16.65 hours. If we travel 36 kilometers per hour, it would take us a little bit less than an hour, 0.925. So let's go ahead and graph these points that we have here. So if we travel, let's see, we said if our rate is 2, and this is really weird because our rate is like our input. So this is going to be our kilometers per hour. And time is actually on our vertical axis, which is really weird. And time is going to be in hours. So a couple points we had here. We know if our rate was 2, our time was 16.5. So that would be, I don't know, somewhere in here between 10 and 20. If our rate was 36, so let's see, 35, 36 would be about in here. We know it would take less than an hour. So I'm just going to make a point over here. Other easy points. Well, if we are traveling at a rate of 33.3 miles per hour, it would take us exactly 1 hour. So that's like a point a little bit above this one. Let's see, if I traveled at a rate of 10 miles per hour, I would get 3.33 hours. So let's go ahead and put that point in about here. If I traveled at a rate of 1 kilometer per hour, it would take me 33.3 hours. So I've got enough to kind of do a graph here. And I can connect all the points because it is not a discrete function. I could travel 10 miles per hour or 10.2 or 10.7, so all the numbers in between. And we do talk a little bit about the graph right here, right? This is exactly what we were saying. For very small values of r, the journey takes a long time. For larger values of r in a fast boat, the trip is shorter. What is t of r when r is 0? Well, we already said that was undefined because we can't divide by 0. What is a reasonable domain? Well, we can't have negatives and we can't have 0. So no negatives or 0. So let's see, our r would have to be something just greater than 0. And I suppose you could say like, maybe less than 100 kilometers per hour. I have no idea how fast boats travel, but there's going to be like an upper limit as well. But r greater than 0 is pretty good for our purposes here. Vertical asymptotes. Unlike the graphs of polynomial functions that look smooth and connected, so remember we had all those polynomial curves in the last chapter, the graphs of some rational functions can look like separate pieces. And that's what we see here, right? Here's part of my graph over here. Here's part of my graph over here. So they really do look like separate pieces, but they do have that kind of interesting curve that we came up with on our example. The dashed line at x equals 3 is a representation of a vertical asymptote. And if you look at what our function is, our function asymptote is this right here. It is 1 over x minus 3. So if you look at that denominator, x minus 3, and then look at where this asymptote is at. My asymptote is at x equals 3. That's because when x is 3, my denominator is 1 over 3 minus 3, or 1 over 0. And that's a problem. We can't have that, right? We can't divide by 0. So that's why we've got that weird behavior at 3. As x gets closer and closer to 3 on the left side, so this would be the left-hand side of my graph. So as x gets closer and closer to 3 on the left side, f of x gets closer and closer to, and that means I'm looking at this right here, this part of my graph, negative infinity. As x gets closer and closer to 3 on the right side, f of x gets closer and closer to, that's this part of my graph right here, positive infinity. It is important to note that the drawn-in asymptote is not actually part of the graph of the function. Instead, it is helpful it is a helpful reminder that the function has no value at 3 and very large absolute values at inputs close to 3. So again, like we said early on, my graph is just these two highlighted pieces, right? But then that line is just kind of showing us how we get close to 3 in between. But we can't actually get to 3 because it doesn't work in our function. So the check your understanding is we're looking for vertical asymptotes. So basically for vertical asymptotes is we're going to take our denominator and we're going to make it equal to 0. That's how we come up with vertical asymptotes. So for vertical asymptotes, it is denominator equal to 0. And that's all it is. So in my first one, when my denominator is x minus 2, I'm going to write x minus 2 is equal to 0. Add 2 on both sides. X equals 2. So think about what x equals 2 looks like. That is a vertical line at 2. That is x equals 2. Next one, I would have x squared minus 9 equals 0, and then I would factor it and make them both equal to 0. Showing all the work here. So we'd have two vertical asymptotes, one at 3, one at negative 3. Next one, take your denominator, make it equal to 0 again. And this time we're going to factor out an x. This one is not perfect squares, but I do notice that both terms have an x. So that's going to be like when I factor out a greatest common factor. I put it in front of the parentheses, write down what's left. The x equals 0 is already solved. And then when I add 6, I get x is equal to 6. So my answers are x equals 0 and 6. So big ideas today. If we kind of go back up to the top here, we can use these rational equations like time equals distance over rate. We can use these kinds of equations to model real life things. The graphs are kind of these interesting curves. We do have to worry about them being undefined. We can't have denominators equal to 0. And we can figure out the vertical asymptotes by making the denominators equal to 0. So I know that we went really quickly through the factoring stuff. If you need help, remember this isn't notes on factoring. This was notes on rational equations and just doing some basic graphs. So if you need help on stuff like factoring, make sure to ask your teacher.